Hi, welcome back to General Chemistry 1. In this video, we're going to talk about ideal gas laws. Before we mention the different individual gas laws, the Avogadro's laws, Boyle's laws, Chaucer's laws, okay, they have different equations. If we combine all of these individual laws to one law, we will have, in terms of math, something like if we combine these two, so we can have Vp over n, V1, P1 over N1 equals to V2, P2 equals to divides N2. And then if we combine the temperature here, then we can have this V1 P1 over N1 T1 equals to V2 P2 over N2 T2. All right, so this describes the relationship with two different sets of gas. Okay, one is in the volume one, pressure one, number one, and the temperature one. And we have another set. If we want to use one equation to describe the gas laws, like all gas laws together, we can use this. PV over NT equals to a constant. In other words, PV equals to constant times NT. It's just different transform of a math equation. So this one, PV equals to constant times NT. If we define the constant as R, that gives us the ideal gas law, PV equals to nRT. Okay, the R here is the universal gas constant. That equals to 0.0821 atm per liter, atm times liter per mole per Kelvin. Also, if we use a different unit set, we can have R equals to 8.314 joule per mole per Kelvin. Okay, so if we use the bottom R, we need to have a unit set of the SI unit. P should in the unit of Pascal, V in the cubic meter, T in the Kelvin, temperature in the Kelvin. If we use the top value of R, we can use the units, atm in pressure, liter in volume, mole, in the quantity, Kelvin in temperature. Okay, so anyway, this PV equals to nRT describe an ideal gas behavior, and it's called ideal gas law. So what is an ideal gas? Not like normal gas you will see. Ideal gas is very ideal. The gas particles has negligible volume. So basically you feel like it only has one point. It does not have volume. And the gas particles are equal sized and do not have intermolecular forces with other gases. They move randomly in agreement with Newton's law of motion. And when these two gases collide to each other, they have perfect elastic collisions with no energy loss. So these are all details like for you to understand. Usually the gases in high temperature and low pressure behave close to the ideal gas. Okay, and in this class, General Chemistry 1, unless specified, all gases are ideal gases. If we don't mention, we have this gas, that means we have this ideal gas. Okay. For PV equals to nRT, this equation, we require you to 100% master this equation. That means not only this equation, you also need to know that you can transform the ideal equation to different format. For example, P equals to nRT over V, V equals to nRT over P, so on and so forth. And you also expect to have a relationship between two different sets of gas to establish a relationship, say P1 over P2 equals to N1 T1 V2 over N2 T2 V1. Okay, something like that. Yeah. Because ideal gas law includes all the previous gas laws, it's your option to either use the ideal gas law to solve a problem or apply individual gas laws to solve a problem. It's just your personal preference. Okay, we mentioned before that gas forms solution. If we have different gases, we can have very nicely well-mixed gas solutions. And for ideal gas, if we have different gas together, we also have a gas solution, and each gas in the gas solution behaves as if it were the only gas present, okay? Assume no chemical reaction occurs. And John Dalton found that the total pressure of a gas mixture, in his case, the humid air, so it has the air and also the water, right? That equals to the pressure of dry air plus the pressure of water. So Dalton's law of partial pressure is, in a mixture of unreacting gases, the total pressure is the sum of the partial pressures of the individual gases. In other words, the total pressure equals to P1 plus P2 plus P3. Okay, if we have a gas mixture, there are pressures caused by each individual type of gas. We can use ideal gas laws to calculate those individual gas pressures and add them up, and we can get the total pressure of this gas solution. Okay, so if you do a general chemistry experiment, you probably know this device. We can collect gas over the water. So there is a tube. You do the reactions in this tube. The gas is generated going through a thin tube, and then in this tube you have it's filled with water. But when gas is produced, the gas going to the top and push water down, so you can collect a tube of gas. Okay, the gases can be collected over water. The water vapor pressure is 118 torr. According to the stoichiometry calculation, so from a chemical equation calculation, 217 torr of hydrogen gas is collected over water. So what is the total gas pressure in the test tube here? For this question, since the gas is collected over water, inevitably there is a moisture, right? Water pressure here. So there are some, in other words, the gas we collected are wet. So for the total pressure, it should equal to the partial pressure of each individual type of gas. One type is water here, 118. The other type is hydrogen, 217. So you add these two up, the pressure in the tube is 315 torr. Okay. When we talk about gas, we talk about ideal gas pressures. We need to talk about standard conditions. Okay, so for standard conditions, it means whatever gas or whatever thing is at 0 degrees Celsius, that equals to 273 Kelvin, and also under 1 atm, 1 atmospheric pressure, 760 torr. Okay, so and when we talk about gas under standard condition, if we're giving you the degree Celsius, sometimes in the you need to convert that to Kelvin in the units of Kelvin in order to use the ideal gas law equation. So just a reminder, when you need to convert temperature in degrees Celsius to Kelvin, you need to add 273.15 to the value of degrees Celsius to get the Kelvin. Okay, and for gas under standard conditions, because the temperature and the pressure are fixed, PV equals to nRT, right? So that means the volume is fixed. Okay, so for any gas under the standard condition, 1 mole of those gas, the standard molar volume, equals to 22.4 liter. Okay, so for any 1 mole of gas under STP, standard temperature pressure, the volume is 22.4. As you can see here in the schematic, we have helium, we have nitrogen, we have oxygen. If we have 1 more of these gas under standard conditions, the volume will be the same. But the number of gas will be the same, the mass will not be the same, the density will not be the same, but the standard molar volume will be the same. Okay, so for this chapter, we talk about gas laws and ideal gas laws, and there are many equations. So of course, we'll have those word questions and need to do some numerical calculations, I would like to summarize all the equations we can use for the numerical calculation. Okay, starting with the ideal gas law, PV equals to nRT, that N is number of moles, right? So when you talk about number of moles, we can establish the relationship between number of moles and mass. Use the mass molar mass conversion. You can, if you see the mass, you can get number of moles, right? Also for the V, the pressure, the volume. Volume should remind you the equation density, right? So density times volume equals to mass. Once you know the density, you can get the volume from the mass. And these two masses sometimes can be correlated to each other, right? For example, if you're provided with a density and provided with number of moles, then you can use mole mass conversion to get a mass first and then get a volume. Okay, so from this number of moles, besides this mass and mole conversion, we can also get number of moles from the molarity times the volume of an equation. We can get the moles from entity divides the Avogadro's number to get number of moles. We can also get a mole from a stoichiometry calculation of a chemical equation to get a mole of product or reactant, right? So there are many ways to calculate number of moles. For this volume, further, we can calculate the volume from, the shape of the material, say the shape of a container that include gas inside. So for the volume, usually the equation is given. It can be a cube, it can be a sphere, or it can be a cylinder. So either ways, we can use those equations to calculate volume, and volume can also, linked with each other or other questions. No matter what type of question, numerical question you encounter, please make sure you are familiar with this basic arithmetic math and also unit conversion and significant numbers. Sometimes it's related to dilutions, ionic equations. So these things can be mixed together with all the equations we mentioned in the slides. So I'll take two examples in our next slides. One is the ideal gas law equation with stoichiometry. The other is ideal gas law equation with the density. So let's take a look at them one by one. For example, how many grams of potassium chlorate decompose to potassium chloride and 638 milliliter of oxygen at 128 degrees Celsius and 752 Joule? Okay, so there's obviously a chemical equation involved. It asks, so it's potassium chlorate decomposition to potassium chloride, right? It asks how many grams of potassium chlorate, the reactant, and it gives us the information of one product, oxygen, 638 milliliter of oxygen and 28 degrees Celsius and 752 Joule. Okay, so the first layer of this question is stoichiometry calculation. We can get information, we know the information of a product and we want information of a reactant. But for the stoichiometry calculation, we usually need the number or the moles of product. In this sense, in this case, it does not give us the mole directly. Instead, it gives us the volume, temperature, and pressure. Okay, so from this point on, if you see the numerical question involving a gas, and you have the volume, temperature, and pressure, or the moles of a gas, in your mind, you should recite the PV equals to NIT ideal gas law equation. Very likely you'll be able to use that. in this case, yes, we're going to use the ideal gas law equation, PV equals to nRT, to calculate the number of oxygen gas, or the moles of oxygen gas. So first, calculate the moles of the oxygen, PV equals to nRT, and then transform that, N equals to PV over RT, right? Then we can insert insert the values and take care of the unit conversion. So for the R we're going to use here will be the ATM, the more commonly unit set, the common unit set R. Okay, so we need to convert all the other units, pressure, volume, temperature, to the common units. So 752 torr will be converted to ATM. Volume will be converted to liter. Temperature should convert from degrees Celsius to Kelvin. Okay, then we can do the calculation. Plug in the numbers in the equation. N equals to PV over RT. Plug all the numbers, and we can get the N equals to 0.0192 mole. Okay, the R we used is 0.0821. Okay, now we know the moles of oxygen. Then go to the stoichiometry calculation that we're familiar about. Write out the chemical equation, balance the chemical equation, the decomposition reactions. Assume there are X moles of the reactant is decomposes. Then establish the ratio. Chlorate over oxygen, according to the chemical equation, is 2:3 ratio. And now in the reality, we have X moles of the reactant and 0.0192 moles of the oxygen produced. So then solve this equation by cross multiply. The X equals to 0.0128. Okay, so in other words, we have 0.0128 moles of potassium chloride. However, it asks how many grams of potassium chloride, right? So we need to do the final conversion, use a mass mole conversion to get the mass of the potassium chloride. Use moles 0.0128 times molar mass of the potassium chloride here, 122. Then we get 1.57 grams. That's how many potassium chloride we have. So for this question, we look at it again. It involves ideal gas laws, involves unit conversion, involves stoichiometry calculation, and also mass mole conversion. So multiple equations coming together, mixed together to solve this one. All right. So let's take a look at another question about density. Ideal gas law involving density. Okay. The density of a noble gas is 2.71 gram per liter at 3.00 atm and 0 degrees Celsius. Identify the gas. Okay. When we say identify the gas, we need to find a unique property of a gas. So considering the problem we have, we can identify the gas, and also it's a noble gas, right? So we don't have many choices of noble gas. The differences are, you may think about number of protons, that's true, but we cannot easily get that from this, this question. So another thing we can get, another property can use to identify the noble gas is the molar mass. Different noble gas have different molar mass, so we can use that as a property. In other words, the question asks you to calculate the molar mass of a noble gas. It gives you the density, pressure, and temperature. Okay, so first, we can find which equation to use. Okay, molar mass equals to mass over number of moles, because the molar mass is what we want to find in the ideal gas, in the noble gas. So molar mass equals to mass over number of moles. Mass, that equals to density times the volume. Okay, so density is something we know. Volume is not. Number of moles is not. Okay. If you're familiar with the ideal gas law, the V over N, that section can be calculated from the ideal gas law. So if you reverse multiply the ideal gas law, we can have P over N equals to RT over P, right? So remember PV equals to nRT. So if you do the cross multiply, PV equals to nRT, right, from this ratio. So V over N equals to RT over P. Plug in that part. We can have the molar mass calculation that equals to density times volume over number of moles. That equals to D times density times RT over P, the pressure. So density is something we know. R is the universal gas constant. T is the temperature, something we know. P is the pressure, and also something we know. So then we can now calculate the molar mass of this noble gas. Okay, again, when we use R, we need to convert all other units, or we need to at least check if the units meets our standard. In this case, density is gram per liter. Okay, T is in degrees Celsius. We need to convert that to Kelvin. P ATM, which is good. So let's do the unit conversion. As you can see, R equals to 0.0821 ATM times liter per mole per Kelvin. So we need to convert the temperature to Kelvin. That is 233.15 Kelvin. Okay. The density does not need to be converted. The gram per liter is fine because liter, of course, is used in R, and the gram is corresponding to the molar mass. If we use a gram, we can get number of moles, so the gram is good. Then plug in the numbers and do the calculation. Okay, molar mass equals the density 2.71 gram per liter. I'll write liter in the bottom, right? It's the same thing. Times R, 0.0821 ATM, liter per mole per Kelvin. Again, I put per mole per Kelvin in the bottom. And then the temperature, 273.15 Kelvin. The pressure is ATM, 3.00 ATM. Then you can cancel out a unit. What left over is gram per mole, right? So it's 20.26 gram per mole. Then we are good. When the molar mass is in the gram per mole, we can use that to identify which noble gas it is. The molar mass of helium is 4 gram per mole. Neon is 20.1 gram per mole. Close enough, okay. Argon is almost 40, and then krypton is 84. So, and we have heavier and heavier gases in the bottom. So according to the molar mass, this noble gas is helium. All right, so this is the end of this video. Hope you are getting familiar with calculations involving ideal gas laws. I'll see you in our next video. Bye.